Today's lecture is on my favorite data structure. They're called Splay trees. And Splay trees are a kind of balanced binary search tree. Kind of like a 2, 3, 4 tree, but with many important differences. So Splay trees are structurally identical to just binary search trees. So in a sense, they're not really a different data structure so much as a different algorithm. But they're simpler than 2, 3, 4 trees, except that they're much more complicated to analyze and understand why they stay balanced. But to implement, they're simpler and faster and are, in my opinion, the balanced data structure of choice in practice for real-world programming. Now, in a Splay tree, all operations take big O of log n time on average. What do I mean by on average? Well, I do not mean the same thing I mean when I say that hash tables take order 1 time on average or quicksort takes n log n time on average. I mean something different. There's no randomization in Splay trees. They're not random at all. What's interesting about Splay trees is that some of the operations can be very slow. So you're not guaranteed that every operation will take log n time. In fact, a single operation could take linear time in the worst case. Where n is the number of items in the tree. So that sounds pretty bad, except for the fact that we come back to the fact that even so, they take log n time on average. So what do I mean by that? How do I reconcile these two things? Well, I can guarantee you that any sequence of k-Splay tree operations, when you start from an empty tree, and with the tree never growing larger than n items, if you satisfy those conditions, you're starting from an empty tree and never have more than n items in the tree, then a sequence of k-Splay tree operations takes at most big O of k log n time in the worst case. So what this means is that you can have a few operations that are very slow, but most of the operations will be so much faster that they'll balance out in the end, and you'll always get average log n time or better. Other nice things about Splay trees, besides the log n time, is that they're much easier to program than 2, 3, 4 trees. And they can often be quite a bit faster, because one of the things that Splay trees do well is they give you fast access to data that you've recently accessed. Splay trees have a kind of memory that way. So if you have a program where you're working with a large tree, but there's a small number of favored data items that get accessed over and over and over again. Those items are going to be accessed much more quickly than the items that don't get accessed very often. So for instance, if you have a Splay tree with 1 billion items, but there are just 10 items that you access frequently over and over and over again, each time you access one of those 10 special items, it'll be accessed in order one time. So this will actually be faster than a 2, 3, 4 tree for when you have, certain items that you favor a lot and you're mostly ignoring the rest of them. So Splay trees are probably the most used data structure invented in the last 25 years. And the people who invented them won something called the ACM Kanellakis Theory and Practice Award for them because they're used so much in industry for so many things. The basis of Splay trees is the idea of doing something called a rotation. So this is how you keep a tree balanced. Binary trees there's actually a bunch of different kinds of balanced binary trees that use rotations to keep them balanced. There are ones called AVL trees and ones called red-black trees. But Splay trees, I think, are the most useful of all. And all these types of trees are kept balanced with rotations. We saw one kind of rotation in 2, 3, 4 trees, and in binary trees, rotations are just as simple or simpler. Here's what one looks like. Suppose you have a key y with a left child x, and they might have whole subtrees underneath them. So here's a subtree A of keys that are less than or equal to x, and here's a subtree B full of keys that are between x and y. And here's a subtree C of keys that are greater than or equal to y. Well, you can do a rotation to the right, which makes x the root of this subtree. And that looks like this. When you rotate right, x becomes the root, y becomes its right child. The subtree A is still the left child of x. The subtree C is still the right child of y, but the subtree B gets moved, so now it's a child of y instead of a child of x. But still, you can see that the binary search tree invariant is obeyed because B is the set of all keys that are greater than or equal to x and less than or equal to y, and that still works out here. So that's what a rotation to the right looks like. And sometimes you do the mirror image, which is a rotation to the left. We're going to build up an algorithm for rebalancing trees entirely out of rotate lefts and rotate rights. Any questions so far? Yeah? Well, that depends on what's in all the subtrees. So maybe A is a subtree with hundreds of nodes, and maybe C is empty. So it all depends. We'll see a bunch of examples of trees being rebalanced by these rotations. Other questions? Okay. So I do want to warn you that Splay trees are not kept perfectly balanced. So one of the principles of a Splay tree really is that keeping a tree perfectly balanced, like a 2, 3, 4 tree, is hard work. And if you try to keep the tree semi-balanced, but maybe not always perfectly balanced, you can actually wind up with a faster algorithm in the long run. So this is one of the reasons why Splay trees don't always guarantee log n performance on every single operation, while you might have a worst case time of linear time for one operation, but that happens so rarely that it's more than counterbalanced by all of the operations that run extra fast, because the Splay tree rebalances itself whenever you have an expensive operation. So let's look at the Splay tree operations. And Splay trees have all the same operations that binary search trees have, and we're going to spend most of our time just looking at how to do the simplest or the easiest one, the find, and then once we know how to do that, all the other ones will fall right in line. So we've got a find operation where we give it a key k and say, please try to find the entry that has that key. Now, this find operation is going to begin just the same as it does in a regular binary search tree. So we begin by finding the item. In other words, we walk down the tree, using the search key to decide whether to go left or right at each node as we walk down the tree, until we get to an entry with the key that we're looking for. Or sometimes we reach a dead end because the key k is not in the search tree. Now, in either case, whether we found the key k or whether it's not in the tree, we're going to let x be the node where the search ended. Whether we succeeded or not. Now, what we're going to do next, here's where we depart from a regular, ordinary binary search tree, is we're going to take that node x and we're going to splay it up to the root of the tree by a sequence of these rotation operations. So again, x becomes the root. Now, why are we doing this? Well, we're doing it for several reasons. Reason number one is if we're accessing the same key, k, over and over again, by moving it up to the root, that ensures that every subsequent time we search for k, it's going to be really fast, because the thing we're looking for is up near the root. So this is the reason why if you're looking for the same few items over and over again in a Splay tree, you're always going to have super fast performance because those items are always close to the root. Another reason is because sometimes Splay trees can become unbalanced. It's usually only a temporary state. And when you find yourself walking deeply down the tree, maybe having to walk more than big O of log n levels down the tree, this is going to rebalance the tree to prevent that slow operation from being able to happen again. So let's look at the ways that we use rotations to rebalance the tree, because it's a little bit subtle. You have to be careful to choose the right rotations at the right time. And to do that, we're going to divide it into 3 different cases. All right, case number 1 is when the node that we're looking for, or the node that we're splaying up to the root, x, is a left child of a right child. or if it's a right child of a left child. So this case is pretty simple. We're just going to take x and rotate it up twice, which brings it 2 steps closer to the root. So let's look at what this looks like. Maybe this is the grandparent, this is the parent, and this is x. So in this case, x is a right child of a left child. And here are the subtrees. Some of these might be big, some of these might be small. We proceed in 2 steps. First, we rotate x up through its parent. And that brings us to this case. So that's step number 1. And then we just do it again, except this time we're rotating x up through what used to be its grandparent. And so that brings x 2 steps closer to the root. Now, this case is often called the zigzag case. To denote the fact that it's either a left child or of a right child or a right child of a left child. Now, if you have the mirror image, like if instead of x being a right child of a left child, if x were a left child of a right child, it would be the exact same sequence you see here, except in mirror image. So, take the mirror image of this tree, mirror image of this tree, mirror image of this tree, same operation, just in reverse. Any questions about the zigzag operation? All right. Second one is almost the same thing, except that there's a very subtle and crucial difference. So keep your eyes open for that, because if you don't notice the difference, you'll do the Splay tree wrong. Case number 2 is if x is a left child of a left child, or if x is a right child of a right child. What happens here is, well, let's take a look at it. Suppose it's a left child of a left child, and the tree initially looks like this. There's the grandparent and the parent of x, and we'll give them all subtrees, as usual. Okay. Once again, we're going to get x up 2 steps in the tree, or up 2 levels in the tree, by doing a sequence of rotations. But there's a very crucial difference here, which is we're going to start by rotating through the grandparent first. We're going to look up 1 level and rotate the parent through the grandparent before we rotate x. And that's different than the zigzag step, and this difference is totally crucial to the algorithm working. So, from there, the parent moves up, replacing the grandparent as the root of this subtree temporarily. And there's x. And then, once we've done that, now we can move x up through the parent with the second rotation, and that gets x to the root of the tree. And this step is called the zig-zig step. So zig-zig is just a way of reminding you that it's either a left child of a left child or it's a right child of a right child. But the zig-zig step is the counterintuitive one. It's the one where you rotate through the grandparent first and then the parent second. So you're sort of reversing the order of those two rotations from what you would expect. Any questions about that? Yeah. You're right, it hasn't changed the depth of the tree. But in a minute, I'll give you a demonstration of why this is a good idea anyway. So I'm going to try to finish this algorithm first, and then I'll give you an example of it, a few examples of it in action. Yeah?
If potentially we were searching for X, and X's grandparent was not the root of the tree, but its great-grandparent, for example, we still start at the grandparent, or we start at the great-grandparent?
On a zig-zig, you're always just looking at the grandparent of X. You're never looking more than 2 levels up the tree at a time. So what you'll do is you'll look up 2 levels. You figure out whether you're a left child of a right child or a left child of a left child or whatever. You do either a zig-zig or a zigzag, depending on that. And only then do you even consider looking at the node that used to be your great-grandparent.
Well, let's say that you're like 4 levels deep. You do a zig-zag,
Mm-hmm.
and then you go look again, and then you'll perform a zigzag, and you'll perform things until it's root.
Exactly. So if you're 4 levels deep, you just look at 2 levels up, decide what to do those 2 rotations. Now you're 2 levels deep. You look again at what your 2 parents look like, or your parent and your grandparent, and again decide which operation to do. Yeah. So as we just discussed, the way this works is you've got these 2 operations and you keep repeating them over and over again. And so you just keep repeating those 2 types of steps over and over again, zig-zig and zigzag, until either you get to the root or you get to the child of the root. And once you get to the child of the root, obviously you're not a left child of a right child, nor are you a left child of a left child. You're a left child of the root. And so that's why there's one more step, is when you're an odd number of levels down, we have to finish up somehow. And we finish up with just 1 simple rotation. So the third possibility is that X is just the child of the root. And we handle this in the simplest way possible with just 1 last rotation. So maybe the tree looks like this, and so you rotate up, X up through its parent. And now the tree looks like this. And this third kind of step is, for obvious reasons, just called zig. Question about that? All right, let me work out a couple of examples so you can see specific trees in motion. Let me do a find 7 on this particular tree. It's a somewhat elaborate tree, but it's going to allow us to try out all 3 of our moves. So the first thing you do is, just like in a normal binary search tree, you start walking down the tree. 7 is less than 11, greater than 1, less than 9, greater than 3, greater than 5. Well, we found the 7. And now you look at what is that 7? Well, the 7 is a right child of a right child, so we're going to do a zig-zig step. And a zig-zig step means you rotate through the grandparent first. And then you rotate through the parent. Well, you rotate X through the parent. And so I'm going to do both of those in one step here. So the upper part of the tree remains the same. Well, except for that part. Up to there, everything's the same. But now the 5 rotates up through the 3, and then the 7 rotates up through the 5, and the 7 winds up here. And that's what our next tree looks like. The 7, you can see, has moved 2 levels up the tree from where it was before. And now the 7 is a left child of a right child. And that means now we have to do a zigzag step. And a zigzag step, you do the intuitive thing, which is you just rotate 7 through its parent once, and then you rotate 7 through its new parent again. And that brings us to here. Now 7 is going to make it up to be a child of the 11. And that's our new tree. And now since 7 is just the root, the child of the root, we finish off with one final rotation, or a zig step. And that's our final splay tree after doing a find operation on 7. Question? Yes? Well, I'm not sure exactly what you mean by using an array, but you only have to change the child pointers of the nodes that you actually visit. And that's only going to be proportional to the depth that you search to. Right. Mm-hmm. Oh, well, I wouldn't do that. No. I would, whatever representation I would use, I would definitely want child pointers to do this. Like the binary heap representation just doesn't make sense for this data structure. Other questions? So let me give you one more example that shows why we do things differently on the zig-zig. Why do we rotate through the grandparent first? So this is going to be hard to copy because I'm going to keep pasting and redrawing things. But ask yourself, what happens if I insert the numbers 1 through 9 into a splay tree in order? Well, first I insert a 1. Then I insert a 2 and splay it to the root. Then I insert a 3 and splay it to the root. Then I insert a 4 and splay it to the root. And so on. And I think you can see where this is going. This is how you can build, or this is one way you can build, a very unbalanced splay tree. And so if you've been wondering why some splay tree operations take theta n time in the worst case, well, this is why. I can build up a tree that's really, really tall. Well, I'm going to start this from scratch. I can build up a tree that's really tall. And now if I do a find zero operation, well, I'm going to have to walk all the way down the tree, and that's going to take linear time. So that's an example of where you can have worst case performance for one operation. But keep in mind that when we were building this tree, it only took big O of one time to insert each new node. So we saved a lot of time building the tree, and now we're just using some of that saved time on this one expensive operation. But suppose our tree looks like, let me throw in one more node just for clarity, like this. And suppose I do a find one operation. What's going to happen when I do find one is a bunch of these zig-zig steps. And each zig-zig step is going to take the parents and rotate them through the grandparent. So at first, you rotate the 2 through the 3 and the 1 through the 2, and you wind up with this hanging off of the 4. Then you rotate the 1 through the 4 and the 5, starting with the 5, and you get something like this. Sorry, 2, 3. That's right. 0. And you keep on doing these zig-zig steps, and every time you do another zig-zig step, you collect 2 more of these guys off to the side. And when you're done, the find one operation, your tree is going to look like this. So you can see if you do this with a really, really tall tree, you're going to cut the height of the tree roughly in half, because you wind up doubling up these numbers along this branch of the tree. But if I didn't use the zig-zig rule where I rotate through the grandparent first, if I were just to be lazy and always use the rule that I just rotate through my parent every single time, then what you would get instead is this. And so if we didn't have the zig-zig rule, we would not rebalance the tree at all. And then I could do a find 10 operation, and the find 10 operation would take theta n time, and it would give us back to this tree. So if you don't remember the zig-zig rule, you're not going to have a tree that rebalances itself. The zig-zig rule is absolutely crucial. And one thing that you can figure out, if you look at each of the 3 different kinds of steps, the zig-zig, the zigzag, and the zig, and see how they work, it's pretty easy to see that suppose you have a node that's on the search path, initially at a depth of d, on the access path from the root to the thing that you're finding. Well, if you look at each of these rules, anything that is underneath x in the tree moves up at least one level for each zig-zag step or for each zigzag step. So, for instance, here, A and B are both descendants of x. They each move up at least one level in the tree for each zig-zag step, and likewise for each zigzag step. So if you're lucky enough to be underneath x, then you get to rise up through the tree with x at least half the speed that x does. And any node initially at depth d on the access path from the root to x moves up to a final depth, when all the splaying is done, of less than or equal to 3 plus d over 2. Now, I would love to give you a formal proof that splay trees actually do what I say and take log n average time no matter what. And there is a proof of that in Goodrich and Tomassia, but I have to tell you that it's a lot of math. You crunch through it, and you get no enlightenment out of it, really. So I'm not going to go through the proof. I'm just going to ask you to trust me. Yeah, question? Yes, you do a splay on every operation. So I will go through the rest of the operations in a moment. Any other questions before I do that? Yeah.
I don't understand why the tree would look this kind of unbalanced. If you said instead of doing zig-zag, we started with the grandparent.
Yeah.
If you guys started directly with the parent, why wouldn't it be 1's right child be 10, and then 10's left child be 9, 8, 7?
Oh, you know what? I think I did this wrong. I think you're right. How would it look?
Because I think we would.
Yeah, you're right. I'm sorry. I did it wrong. I think it comes out like this. That's it. But still unbalanced. Other questions? Okay. All right, so now that we know how to do find operations, it's pretty easy to explain the other operations because they're exactly like binary search tree operations, just the operations we already know from ordinary binary search trees plus splaying. So, for instance, if I want a method that finds the first key or the last key, or you could call these max and min if you prefer, the minimum and maximum key in the tree, then do it the usual way. Like if you want to find the entry with the minimum key, you just keep following left child pointers until you run out of left child pointers. And then once you've found the entry with the minimum or the maximum key, you splay it to the root. That's it. When you want to insert a new entry into a splay tree, with a key of k and an associated value of v, so we're using our usual entries with a key and an associated value, you insert the new entry kv into the tree exactly the same way you do with an ordinary binary search tree. And that creates a new node that's a leaf of the tree. And you take that new leaf and you splay it to the root. That's it. And finally, the remove operation. I want to remove from the tree the entry whose key is k. I'm going to start off exactly the same way as I do with a regular binary search tree. Now, you might remember that the remove operation with an ordinary binary search tree is a little bit complicated because if we want to remove a key that has two children, we can't actually remove that node. We have to find the next highest key, remove its node, and move its entry up to replace the old entry in a higher node. So remember, the remove operation was a little bit complicated. And so we have to take that into account here. The important thing is that some node is removed from the tree. Call it x, and x is not always the node that contains the key k. It might be the node containing the next higher key. But if the key k is in the tree, some node gets removed, and that node's parent is what gets splayed to the root. So for instance, here's a sequence where we do remove 2 on a tree where 2 has 2 children. So what happens, you'll recall, is that since we can't just plug the node containing 2 out of the tree, it has 2 children, we find the next larger key after 2, and we move it up to the top of the tree to replace the 2. Well, the node that got removed from the tree is not the 2. The node that got removed is this node down here. So I'm going to call that x. And now x's parent is the node that gets splayed. So it's the 5 that's going to get splayed, and here we do a zigzag. And our final tree looks like this. Any questions about that? Yeah. It's true that the minimum key will never have a left child, but still, if you're in a situation like this, now suppose I take this tree and I do min over and over and over again. I keep asking for the minimum key, or calling the first method. Every time I call the first method, I'm going to have to walk all the way down to the 0. And if I'm not rebalancing the tree, then that's going to take linear time every time. But if I am rebalancing the tree, every time I do that, then the first time I'll have to walk down n levels. The second time I'll have to walk down n over 2 levels. The third time I'll have to walk down n over 4 levels. And before I know it, the tree has rebalanced itself, and it's only log n levels deep. So it's always important to rebalance the tree no matter what operation you do, because you might have found a really deep part of the tree, and you don't want to allow that deep part of the tree to continue to exist for operation after operation. Yeah?
Okay, so you said x is the node but you called it 2, but you said x is 4. Is that because 4 was the node that actually was getting changed?
That's right. So the node that contains 2 is still in the tree, and it just contains a different entry. This node is the node that actually went away. So it's the node that actually went away, and not the key that went away, that we care about when we decide who gets splayed. Other questions? Okay. Well, I just have one last note then, which is sometimes you try to remove a key, and it's not in the tree. So if the key you try to remove is not in the tree, well, just like with a find operation, you still have to splay something. And the reason you still have to splay something is, suppose I took this tree and I did a remove -1. Well, it would walk all the way down here only to find out that there's no -1 in the tree. Well, if I did remove -1 over and over and over again, that'd take theta n time every time. So I have to rebalance the tree even if I didn't change it. So if I try to remove a key and it's not in the tree, I still splay the last node that I visited while I was looking for k. So as usual, I splay that node to the root. And that's it. Any final questions? Yeah.
Just a general question.
Mm-hmm.
If the node that you want to splay is, let's say, a right of a left of a left,
Uh-huh.
and what it should do is go zigzag and then zig to the root.
Uh-huh.
Would you instead do a zig and then a zigzag to the root, or would that be wrong?
You know, I honestly don't know whether that would work or not. I would have to go through the mathematical proof and spend several hours cranking equations to figure that out. So, just to be safe, I'd stick to this formula.